Hello, my name is Augusto, and I'll present our work entitled An Automatic Flow for Precise and Approximate Synthesis. This work was developed by Isaac Souza Campos, myself Augusto, Bruno Abreu, Matheus Grellert, Joana Carvalho, and Cristina Meinhardt. We are all from Brazil, from the Federal University of Santa Catarina and Federal University of Rio Grande do Sul. This is an outline of my presentation. I'll start by presenting an introduction and motivations of our work. Then I will present the decision tree Boolean synthesis, the automatic flow proposed by us, and the evaluation for approximate synthesis, and some final remarks. The advancements of technology nodes creates the need for better logic tools and techniques, which are able to build and develop more complex integrated circuits. This brings challenges to traditional logic optimization tools and techniques. Espresso, for example, a traditional logic optimization technique, is restricted to circuits with at most 20 input bits. There is a trend in the use of machine learning, and this can be explored during the logical synthesis stages. Also, approximate computing can provide promising results too, for example, providing reduction in power in area and power consumption for error-resilient applications. The goals of this work are to propose a logic optimization flow using decision trees. With that, we attempt to automate the logic optimization process and reduce the runtime for logic optimization. Decision trees are a good alternative to optimize logic functions because tree-based methods are adequate for classification problems, which is the case of Boolean functions. Also, decision trees are convenient solutions since their output can be easily transformed into a sum of products or product of sums. Lastly, the algorithm for building decision trees are usually fast since they do not require expensive operations. These decision trees are formed by split nodes, which is a comparison between features and constants, and ending on leaf nodes, which are the final outcomes of the model. Considering a Boolean problem, a feature is equivalent to an input bit, and the comparison are simply checking whether the bit is 0 or 1. Each output node is 0 or 1 as well. To exemplify how decision trees can be used to Boolean optimization, a full adder circuit will be used as a case study. The full adder is composed of 3 inputs and 2 outputs. The table of a full adder is present at the left, as you can see. In this example, we will consider only the sum output bit, and the decision tree results from the training and synthesis is shown in the image as an NAAG, and the expression is in the form of a sum of products just below. As expected, the accuracy for the solution is 100%, since all the mean terms were considered in the learning process. To demonstrate how to learn from an incomplete Boolean equation, we can assume a randomly defined incomplete truth table with half of the full adder mean terms. This reduces the table used to train a decision tree. The training set has then 4 mean terms and for the training and other half for the complete table as used as the validation set. The learned expression and AIG obtained had a reduction in the number of nodes and literals in the expression. However, as you can imagine, it will impact the accuracy of the solution, giving us an approximate circuit. Now I'm going to show you a comparison between the classical tool Espresso and our decision tree Boolean optimization. We used 90 benchmarks to run this comparison. First, we run Espresso for the 90 PLAs and then kept the results to compare at the end. Then we parse each PLA to decision tree inputs. That's because the tool we are using, C5.0, needs 3 different inputs to be able to run the learning process. With these inputs, we can generate a tree. With the tree file ready, we have to convert it into an EQN format. We need this format because the ABC tool, which is the tool we're going to use to extract information about the circuit, only reads EQN formats, since ABC isn't able to read decision trees. The EQN format is a convenient since we can easily transform decision trees into an EQN file, and I'm going to show you how to do so. This is an example of a C5.0 tree output, and this example we are going to transform this into a product of sums. So the first thing to do is to consider only rules that are from class 0. If we were making a product of sums, we would consider class 1. But in this case, we are going to make a product of sums, so the first rule is a class 0. You can see here the x3 equals 0, so we put in the equation the value of x3. Uh, x4 equals 1, so we put in the equation the value of not x4, and we just repeat the process for the whole file. So x5 equals 0, x6 equals 0, x9, and we have the equation. Now we can consider the other rules also, like rule 2 here, which is also a class 0. So we have x4 or x5 or x7 or x8 and not x9, since x9 equals 1. For the example that I just showed you, we use product of sums, but for this flow of comparison, we use the sum of products, which is very similar. Now we can evaluate the final circuits with ABC extracting the data needed to make this evaluation, which were the number of nodes and accuracy. To calculate these results, we made the number of nodes over the accuracy result, which gave us 10.21 for espresso and 0.75 for C5.0. In this case, the lower the result, the better. And here we also have the average number of nodes and accuracy for espresso and C5.0, considering 90 benchmarks. To be sure that our decision tree approach is a good alternative, we decide to compare other methods with it. So this workflow represents the methods that we were compared with the decision tree approach and will be presented next. We call these three methods as direct verilog, which is the simplest and most direct way to obtain the synthesis result, ABC optimization script, and the decision tree training for logic synthesis, which is our approach. Three tools were used to help the automation process, such as the ABC, which is a public domain tool for logic synthesis. It is based on on AND inverter graphs. It was used to make conversions and optimizations, basically. C5.0, which is a decision tree implementation. Quartus, which is a software to design FPGAs used in the FPGA synthesis, and Janus, which is a software used to make ASIC synthesis. The three methods shown here were compared so we could understand the impact of the decision tree on the final results, no final resulting circuits, and compare our approach. The direct verilog synthesis method uh, analyzes the native logic optimization of commercial tools. All methods have some steps in common. One of them is the output split. It is necessary because ABC does not accept PLAs with more than one output bit. This step is the first thing to run in this method and also in the next ones to be presented. This first method seen on the screen was called direct verilog synthesis because it basically reads the PLA file that represents the truth table and converts it directly to Verilog. ABC and Quartus both uh, both provide their own optimization during these steps. The second method is the ABC optimization script. In this case, after reading the PLA, ABC converts the file to AG format in order to use the compress to RS optimization. After this optimization is done, it converts the AG to a Verilog file that will be synthesized by Quartus, such as in the previous example. The last method is our proposed approach on decision tree training for logic synthesis flow. Here, after we got the decision tree output after the learning process with C5.0, it is transformed into a sum of products as the EQN format. then it is read by the ABC and converted into AIG afterwards. Sorry, and afterwards into a Verilog. We need this AIG intermediate format because some of the values of the results for the final comparisons are in this format. We used two benchmarks to run by the methods. Both of them are composed of complete truth tables, but the decision tree synthesis can provide an approximate computing logic as demonstrated by our analysis. After splitting the outputs to run the synthesis flow, they can present different accuracy results. The accuracy of the analyzed benchmarks outputs can be seen on the right. The decision tree accuracy is 100% for most of the outputs on the LU4 circuit, despite two outputs that are limited to 98.1 and 99.3%. The decision tree accuracy for the PDC circuit presents only one output with less than 99 accuracy, and the majority of the 40 outputs reaches over 99.5. The impact of loss in accuracy is highly dependable on the application. In this image, we can see the ASIC synthesis result. Here we have the results for the benchmark LU4 in yellow and PDC in blue, and the tree methods with table lines, such as the decision tree, the ABC script, and direct Verilog. For the LU4 benchmark, we had a very close area to the other two methods, and also the total power was very close to the other two methods. But for the PDC, we had a considerable reduction in area and also a considerable reduction in total power. Now for the FPGA synthesis, we were not able to get the power consumption, but we were able to calculate the area and delay. The area is calculated by the number of lookup tables of the FPGA. So we have a 275 versus 600 and 588, and also a 26 versus close to 100 on other methods. So it's a very good improvement here. So concluding this presentation, this work evaluates the impact of adopting decision tree logic synthesis flow to reduce circuit power, area, and delay. The current decision tree flow can be explored to generate more power efficient solutions at the cost of a tolerable level of accuracy depending on the application. As future work, we'd like to expand our evaluation to a larger set of benchmarks. We are also trying to integrate our flow with open road synthesis flow, and also explore other decision tree tools such as sklearning. And that's it for my presentation. Thank you for your attention.